We're going to start promptly. We are about to finish section 2.5. We still have to prove the Bolzano-Weierstrass theorem that we stated last time, although we provided an idea of how the proof could go. So we'll get to that. But before that, let me remind you, as I said last time, so we're going to have a quiz during class time next class. And it will be about sections 2.4 and 2.5. All right, so we'll have a quiz and it will be about, you'll do it during class time. And this time it will be of a form where you will write down, so it will not be a quiz like multiple choice type of quiz. It's going to be one where you need to write down your solution. If you have done it, I mean, it will be a problem from the homework. So if you have done one your homework already, you may just take a picture of your actual homework and upload it, as easy as that. Okay.
What did you say the quiz was going to be on?
2.4 and 2.5.
Okay.
Yeah.
How long will we have for the quiz?
15 minutes.
And it's only going to be one question.
Yes. Or
okay.
Yeah. Yeah, I think I'm going to have you to choose one of two.
And the quiz is next class?
Yes.
What were you saying about taking your picture about your homework?
Yeah, so it will be a problem from the homework. Or so if you have done it already, maybe you don't need to even do it again, right? I mean, I'm not going to ask you to rewrite what you've written already, so you can simply take a picture of whatever problem I ask. If you haven't done it, then you need to do it in those 15 minutes. So it's like I usually do during class time. I mean, when I've taught this class before, that's what I would do, right? You can bring your homework, and then if I ask a problem, you could have it with you, your homework, and then if I ask you for a problem from the homework, you could simply copy your homework and put it on the piece of paper, and that I will collect. Here, there's no reason for me to ask you to rewrite it, right? You can simply take a picture of your actual homework. That's the point that I was trying to make. And
for practice, we could rewrite it.
Yeah, if you want. Yeah, it doesn't hurt. You have to use the time anyways. Yeah, okay. Any more questions about that? The quiz?
You said it was going to be on 2.3?
2.4 and 2.5.
Okay, thank you.
You're welcome. Good. So let's let me show you the page where we were working with last time. So we have right here the statement of the Bolzano-Weierstrass theorem. It says that every bounded sequence contains a convergent subsequence. We put this remark that the boundedness part is necessary, otherwise here's a counterexample. And we gave an idea of the proof here with this little drawing. The idea was to find a subsequence by always looking at we're going to half, and always look at the part that has the most number of elements, meaning infinitely many, right? Because the sequence is an infinite set. It's impossible for both parts to be finite. If both parts were finite, then the entire thing would be finite, and it is not. So that's what we're going to be doing. So let's start writing that part. So to begin with, so here is the first part is that the sequence is bounded. So assume the sequence AN is bounded by capital M. Consider the intervals negative M to 0 and 0 to M, right? Because our sequence is infinite, one of these two, and these two cover, so let's write that down, because A sub n is a subset of negative mm, which is the union of those two, you'll notice that they overlap at 0, right? So that's not a problem. So if this union doesn't have to be disjoint, but because this is a subset of that and this is an infinite set, then one of these two pieces must have an infinite number of elements of the sequence. One of the two intervals must have infinitely many members of an, right? So and whichever one it is, let's call it, we're gonna call it I1. Put my camera a little bit further up, better. So let I1 be the interval with infinitely many. Okay, and we're gonna select an element in I1, any. I mean, there's infinitely many, so pick one of them, and we're gonna call it an sub 1. Pick an arbitrary element of the sequence in I1. Call it an sub 1. Okay, and then we're gonna repeat this process recursively. So what is it that we're gonna do? Now we're gonna think I1 as the initial interval that we were working with, and we're gonna divide I1 into two equal pieces. So proceed recursively. So we're gonna write here, proceed recursively, i.e. pick or divide I2 into two equal intervals. I mean I1, divide I1 into two equal length subintervals and pick as I2 the one with infinitely many elements of the sequence. Okay, and again, we can do this because we have infinitely many in I1. So when we split it into two pieces, one of the two pieces has to be infinite. Otherwise, both will be finite, and then the entire thing would be finite. And pick n sub 2 in I2. All right? And then we continue. So now we take I2 and we divide it in half, and we pick the one of the two parts, one that has infinitely many elements, and pick an element there, and we call it an sub 3. And then we take I sub 3 and we divide it in 2, etc., right? So I'll just write a little additional sentence here. Continue this process. Continue this process where ik will be one of the halves of ik minus 1 with infinitely many elements of the sequence, and we pick an element nk in I sub k. All right, so that's the setup. Now we need to remember this sequence that we're constructing, an sub 1, an sub 2, an sub 3, etc. That's our candidate for the convergent subsequence. So we need to first define what that limit is going to be, and then prove that it is the actual limit. Okay. So we're gonna do a little bit of accounting of everything that we've done so far. And first, I want to talk about how big is the length of, how big are these intervals, right? Starting with I1. So what is the length of I1? Oh, that's easy, right? How big is I1?
Infinite?
No, not infinite, certainly not. It has infinitely many elements of the sequence, right? But what is its length?
M?
M, right? Because it's either this guy over here, it's the from negative M to 0, or from 0 to M, right? So how big is it? Well, M, right? So the length of I1 is M. How about the length of I2? Well, remember how we did it, right? We took I1 and we divided it into two equal pieces, equal length. Yeah, so it has to be M over 2, right? And then I3 would be half of M2, so M over 4, and etc., right? So in general, the length of I sub k is going to be M over 2 to the power k, right? Okay, so that's a little bit of bookkeeping. And remember, we have an element that belongs to that interval, right? So then, what is this, the limit of, what is this limit? Let's do, what is this limit? So note that the limit, of course, when k goes to infinity, because m is just a constant. What is this limit? Well, we know already that we can use the properties of the limits we learned last time. So this is a constant, we can take it out. So it's this, and we can write this as 1/2 to the k, right? And then we also did this one last time. We said that whenever we have a number b between 0 and 1, and we raise it to the k, that goes to 0, right? So this is m times 0, so this limit is 0. So these numbers are going to 0, the lengths of the intervals, right? What is the meaning of that? Well, it means that for a given epsilon, I can find a k that makes this as small as I want, right? So then, for any epsilon greater than 0, there is some capital N such that if k is bigger than capital N, then this number m over, and you'll notice that I'm going to write it, instead of using 2 to the k, I'm going to use 2 to the k. There's something according to my notes. Oh yeah, I made a little typo here. So the length of I2 is m over 2. That's correct, right? But this one is not correct, right? Because look, with 2, it should be 2 to the first power, right? They don't match. So so the next one would be m over 4, right? So let me write it here. The length of I3 should be 1/2 of m over 2, which is m over 4. So this is not quite right. It should be k minus 1, correct? It's just a little mistake that I was trying to fix. And then of course, then I probably want to do here k minus 1 as well. The limit is still 0, but we want k minus 1 because that's what we are going to use, right? The length of that interval. Okay. All right. Now, we're talking about the lengths of the intervals. At this point, you should be wondering why do we care about the lengths of the intervals? Isn't this about showing that there's a convergence of sequence? And yes, you will be right about that, but to show that the limit actually works, we're gonna need these, all right? So in anticipation for that is that we made this calculation. All right, so what is going to be our proposed limit for this sequence? Well, here's what another important property we have of these intervals. The way we constructed them, note that we have this property. We have that I1, we started with I1, and then we picked one of the two halves. So for sure, I1 has inside I2, right? And then I3 was one of the two halves of I2, so I3 is inside I2, etc., right? Like this. Remember what we call this? We call it a nested sequence of intervals, right? This is a nested sequence of intervals, and they are all closed. So we proved an important property there. What was that important property? The nested interval property. What does the nested interval property says?
Their intersection isn't empty.
Excellent, that's right. So then by the nested interval property, their intersection from 1 to infinity is non-empty. And because it's non-empty, let's pick an element there, right? So let's pick an element there. Let X be an element of the intersection. And now we're going to show that X is actually the limit of the sequence. We will show that A and K, this sequence we constructed, converges to X. Okay, now how are we going to do that? Super easy. In fact, we already done all the work, right? So how do you show sequence converges to something? You pick an epsilon, an arbitrary epsilon, and with that arbitrary epsilon, you show that there is a K big enough such that this difference is smaller than epsilon, right? So let's do it. Let epsilon greater than 0 be arbitrary. Then we're going to use this epsilon as this one over here. So we know there is capital N that makes this happen. By a previous observation, there is capital N such that m over 2 to the k minus 1 is less than epsilon. Right, so we're using this previous observation that I was telling you about. Now you may be wondering why, because then that's what we need. Observe the following. Then this is really what we need. How far is A and K from X, right? But here's the thing. Both A and K and X belong to the kth interval, right? So both, let me write it here, both A and K and X belong to IK by definition, right? A and K belongs to the kth interval and X belongs to all of them. So then how far apart they are is less than the length of the interval, right? See, if you have two elements in 2 points in an interval, the farther apart they can be is if they are the endpoints of the interval, right? And the endpoints of the interval is how you measure the length. So of course, this length is bigger than the distance between these two elements there, right? But what is the length? Well, the length is, we calculated it before, is m over 2 to the k minus 1. And it's positive. We can put absolute value bars or not. It really doesn't matter. So let me just write it here. And we know this is less than epsilon, right? So then there we go. We're done, right? So for a given epsilon, I can find a capital N. The capital N comes from this other limit. And with that capital N, I know that if if little k is bigger than that capital N, then A and K minus X is less than epsilon. So we're done. This finishes the proof. So this means that the limit of the A and K is X. And that's the end of it. So the beautiful result, right? Every time you have a bounded sequence, it contains a convergent subsequence, right? I like this result because it's telling us that somehow, no matter how complicated you want to make things, how chaotic, there's going to be some order, right? Even if you think of a sequence that is totally weird and going all over the place, and that seems very, very chaotic, like I said, you can always find a subsequence that is not chaotic, that it's going to be convergent, right? It's going to have a limit. That's what this beautiful theorem says. And it's not only beautiful, it's useful. We're going to use it a lot, specifically in 2.7, as a matter of fact. But before we do that, let's actually talk more about sequences and subsequences. And so we're going to go now towards the next section, 2.6. And in 2.6, we're going to talk about a new concept called Cauchy sequences, right? So let's write it down here, 2.6. And the it's called actually the Cauchy criterion. Okay, and we'll start right away with a definition. This is definition 2.6.1. And it says the following. We're going to say that a sequence is Cauchy. A sequence, AN, is called a Cauchy sequence. That's a new name we're learning. If for every epsilon greater than 0, there is some capital N, a natural number, such that the following happens. If a little m and little m are bigger than capital N, then an minus am is less than epsilon. All right? That's a formal definition, and now I'm going to give you the feeling. What is the meaning of this? And here's what it is. This is telling us that a sequence is Cauchy if the terms get close and close to each other, right? So I've specified how close I want. That's the epsilon. So think of epsilon as a tiny, tiny, tiny number, like a millionth, 1 over a million, 1 millionth, 10 to the negative 6, right? And my sequence is Cauchy if no matter how small a number you pick, like 1 millionth, you can find a point after which the elements of the sequence will be closer than 1 millionth. So there will be a point, that's the capital N, and after that point, the numbers in our sequence will be close to each other, closer than 1 millionth, right? So that's the feeling. A Cauchy sequence is a sequence in which the terms are eventually getting closer and closer to each other, right? Now let's compare these to our limit definition, right? So I'm gonna put the two of them side by side or next to each other so you can see. So here is in short what it means for an to be Cauchy. For an to be Cauchy means the following. It means for every epsilon, you can find an entry point such that if little m and little m are bigger than that entry point, then this happens. The distance between those two is less than epsilon, right? Now here's the definition of an being convergent to A. It means that for every epsilon, there is a capital N, such that if little n is bigger than capital N, there's only one variable here, then an minus A is smaller than epsilon, right? You see how they are alike? So, but they are alike and different at the same time, right? Here we're saying the two terms are getting close to each other. Here we're saying the terms are getting close to A, to the limit, right? They're getting closer and closer to the A that we believe is the limit. That's how they are different, right? Now,
Professor?
yes.
After the epsilon, on the second one, there's
greater than?
Yeah.
Yes, thank you. Yeah. Yeah, so they're related. And the beautiful thing, I mean, I'm gonna tell it to you right away, is that these definitions are actually equivalent. So that's the purpose of this section, the so-called Cauchy criterion. And this is very useful because what we're gonna learn is that a sequence that is Cauchy is convergent, and that every convergent sequence is Cauchy. So they're equivalent definitions. There are different ways of saying the same thing, and that's very useful because maybe to prove convergence, instead of proving it directly, you use Cauchy sequences, right? You prove that the sequence is Cauchy. Or maybe to you have as a property that a sequence is convergent, and it's more convenient for you to know that the sequence is Cauchy to prove something else, right? So these are more tools to our advantage, right? So That's what we're going to be doing. And let's start with the easiest one of them all, which is the following. The book somehow splits it in two. So the first one we're going to call Theorem 2.6.2. And it says the following. It says that this is the easy one. Every convergent sequence is Cauchy. In fact, this one is, in a certain sense, so easy that the proof doesn't even prove this one. It assigns it, it's exercise number 1 in the homework problems. All right? But let's do it. I mean, it's so easy. It's going to take us 3 lines, right? So let's think about it. What would be the idea of proving this? We have something that is convergent. So we have the bottom definition here. And we want to prove the second one, right? And the obvious idea is to use the limit, that number A, as our middleman, right? It's time to make a little picture here. So here's our situation. So here's somewhere there is A. And we know the elements of the sequence are getting really close to A, right? They're getting close to A, like this. So how can I prove that they're getting close to each other? Well, the way I can prove it is pick any of these two, and I can measure the distance among themselves by going from here to A, and then from A to the other one. And because I can make both of those really, really tiny, then I can make the entire thing tiny. That's the idea, right? And we've seen this idea many times already, where we specify a distance that we want, we put something in the middle, and we split it using the triangle inequality with the other 2 pieces. That's precisely what we need to do here. So here's how it's going to work. Let's go directly and we'll write the proof. So because, assume AN converges to A. Let epsilon greater than 0 be arbitrary. Because AN converges to A using epsilon over 2, right? As usual, you need to give yourself a little bit of room. So we're using epsilon over 2. Using epsilon over 2, we know there is some capital N, a natural number, such that if little n is bigger than capital N, then AN minus A is less than epsilon over 2, right? So we're using epsilon over 2. All right. Now, that's not what we want. We want AN with AM, right? But that's okay. We're going to get it by using A as our middleman. So finally, note that if both little n and little m are bigger than capital N, then if I want to measure how far apart they are, what I can do is I can put the middleman in between, negative A plus A. I can use the triangle inequality. And because both little n and little m are bigger than capital N, then I can use the previous inequality. So this will be less than epsilon over 2 plus epsilon over 2. And we are done, right? What did we prove? I just proved the Cauchy definition, right? The Cauchy definition is there you give me an epsilon, and there's a capital N, such that whenever the 2 indices are bigger than capital N, then the distance among the corresponding terms is at most epsilon. That's it. That's the definition of being Cauchy. And like I said, this is the easy one, right? This is the one that is way easy. The other one is harder. I mean, let's think about the converse. The converse would be that every Cauchy sequence is convergent. And here's where the problem lies. If you have a Cauchy sequence, right, it satisfies the top. And you want to show the bottom one, the first issue you're going to encounter is you're going to be like, well, but what's the limit, right? What is the A? If I don't know the A, how can how can I prove it? Because when someone tells you they have a Cauchy sequence, you don't know what it is converging to, right? So we're going to prove it's convergent. And as part of a proof, you're going to actually find out what the limit is. And that's the harder part of a proof, to determine the limit, right? To determine exactly what the limit is. So as a first step towards that, we need to first establish this other property, and that is that Cauchy sequences are bounded. So this is lemma 2.6.3. And it precisely says that. It says Cauchy sequences are bounded. And this is going to look a lot like the proof we did of convergent sequences are bounded. You may remember that one. We proved before that every convergent sequence is bounded. And the way we did it is we use the limit, and it was like, and we picked an arbitrary epsilon like 1. And then we control all the larger terms and then use the smaller terms and the maximum of a bunch of things. So this may seem familiar. If it seems familiar, it's because it's pretty much the same argument that we did to prove that that convergent sequences are bound. So we're going to pick an arbitrary epsilon, a fixed epsilon. And for simplicity, I'm going to pick 1. So let epsilon equals 1. Because an is Cauchy, then there is some capital N, a natural number, such that if n and m are bigger than capital N, then an and am are within 1 unit of each other. Right? That's what we're using here. Okay? And then if this is true, then in particular, this is a particular case. So instead of using arbitrary n and m, I'm going to use m equals capital N. Right? So using m equals capital N, if little n is bigger than capital N, then an minus a sub capital N is at most 1. You see what I did here? I just used a particular case, right? I can use any 2 numbers that are bigger than capital N. So what I'm doing is I'm using an arbitrary one, that's the little n, and another one that is not arbitrary. It's going to be capital N itself, okay? And this is convenient because then what I'm really after is to bound an, right? Then if little n is bigger than capital N, I can do the following. I can write a sub n in absolute value as follows. I can write it as a sub n minus a capital N plus a capital N. You see what I did there? The classical trick, right? Add and subtract something. Why? Because then by triangle inequality, this is less than or equal than a sub little n minus a sub capital N, which I can control, is right here, is at most 1. And then this guy, which I can also control because this is a fixed number, right? It's just some fixed number. So this is at most 1 plus the absolute value of a sub capital N. And if you'll notice, this tells me that I can bound all the elements that are bigger than capital N. All the elements a sub n, where with n little bigger than capital N, are bounded already by this guy over here. So then I only need to now take care of finitely many others, and that's easy. So finally, set capital M to be the maximum of all of these numbers. This one to begin with, and then all the other ones that I haven't checked, A1, A2, A3, all the way to AN minus 1, all the previous ones. Pick the largest one, and including this other one, right? And then we're done, right? So now, if little n is bigger than capital N, then absolute value of a sub n is less than or equal 1 plus absolute value of a capital N, which is less than m. Good. And if little n is less than capital N, then a sub n is less than m, because then it would mean that this guy is one of these. And if it's one of these, then it's smaller than the maximum. So in either case, we're good. We bounded the sequence, right? It's bounded by this capital M. We are done. All right? Questions? This should be, like I said, very familiar. I mean, we did this argument already, perhaps with a bit more detail when we prove that convergent sequences are bounded. Okay, and this finally gives us the missing tool for us to do the full part of the theorem. So here is the full theorem, theorem 2.6.4. This is called Cauchy's criterion. And it says the following. It says a sequence converges if and only if, love those terms that are if and only ifs, it is a Cauchy sequence. In other words, convergent and Cauchy are the same thing, right? You can interchange one by the other freely. They mean exactly the same thing. All right, now let's write our proof. So if we go this way, meaning we start with a convergent sequence and we show it's Cauchy, guess what? We did that already, right? That was theorem 2.6.2. So this one is theorem 2.6.2. So we did it already. So the hard one is the one we haven't done. We assume it's Cauchy and prove it's convergent. So let's do the backwards one. And let's start by writing our assumption. Assume AN is Cauchy. Now, I want to use our previous lemma. And why do you think I want to use it? Because remember, what was the obstacle for the proof of this theorem? The obstacle is we don't know what the limit is going to be, right? I need to get a hold of some number that I want to say this is going to be the limit. How can I do that? Well, it will help if I have a bounded sequence. Why? Because by Bolzano-Weierstrass theorem, what can we tell about bounded sequences?
Have a convergent subsequence.
Exactly. Yes, they have a convergent subsequence, and that subsequence is going to have a limit. So then maybe I can use that as the limit that I want to prove for the overall sequence. Yes, that's exactly what we're going to do. So by the previous lemma, AN is bounded. Okay. So then Bolzano-Weierstrass theorem applies. Bolzano-Weierstrass theorem. It has a convergent subsequence. Let's call it AN sub k. And now let's give a name to the limit. Let's call it A. So A will be the limit of AN sub k. And that now we want to prove that this is the limit of the overall sequence. We will prove that the limit of AN is A, right? Not only that subsequence, but the entire sequence also goes to A. And the idea is that, okay, so picture time. So here's the picture, right? So we have the real line, and somewhere over there is A. And then we have a sequence and a subsequence of that sequence, right? So we have our sequence here. I'm painting this in red. And then we have some elements of there that are the subsequence, right? So maybe this is the subsequence. We pick this guy and then that guy and that guy. We know the subsequence approaches A, right? Now, if we know the subsequence approaches A, how can we tell that the overall sequence also approaches A? Well, we can use the Cauchy property. The Cauchy property tells me that the elements themselves get close to each other. So we know these guys are getting close to A, but we also know that all the other ones, the orange ones that I drew, have to also get close to the blue ones as the index gets bigger and bigger. So the oranges should also be getting close. The ones that are not in the subsequence should be close to the blue points. And if the blue points are getting close to A, then the orange ones are gonna follow along. That's the idea, all right? That's the idea of the proof. So let's just write it down. And as usual, we need to use the epsilons, and we need to give ourselves a little room. So there are two things we need to use here, that the limit is A and the Cauchy property. So let me start by writing down the Cauchy property. So because AN is Cauchy, then using epsilon over 2, right, there is some capital N1 such that if little n and little m are bigger than N1, then AN minus AM are closer to each other and closer than epsilon over 2. All right? So that's the first property that we want to use. And then we also want to use the limit property, right? So also with epsilon over 2. Similarly, since the limit of A and K is A, using epsilon over 2 again, there is N2 such that if little k is bigger than N2, then A n sub k minus A is smaller than epsilon over 2. All right? Now, how do we combine these two? Well, the usual trick, although we need to be careful to specify exactly what is the n that we need to choose. So here's what we're gonna do. We're gonna pick an nk. So pick an nk. Pick nk such that k is bigger than n1. No, k is bigger than n2, so that we could use this inequality. And nk is bigger than n1. All right, so let me say a little bit about this. It may seem weird. Why am I doing this? Well, I want to use both of these, right, for n sufficiently large. Now, to use the bottom one, I need k to be bigger than n2. But I want to also use the top one because I want to combine them. So to use the top one, I need to know that the index is bigger than n1. So I'm asking for nk to also be bigger than that. Now, is that okay? Is this something that I can ask? Well, yes, right? I can always pick an index as big as I want. So I start by picking some k bigger than n2. And then I check, is nk bigger than n1? If yes, I'm done. Suppose it doesn't happen. Suppose that nk is less than n1. Well, then pick an even bigger k, right? Pick a larger k. And the sequence nk goes to infinity. So eventually we're gonna, we can pick a number big enough that will surpass n1. Okay, so I'm trying to establish why there's no trickery here, that I can really pick this nk. Okay, and then now the final step of the proof is to use this as our m. So using m equals nk, then for n, little n bigger than capital N1, it's all we're gonna need. The following happens. How far apart is an from a? That's what we want, right? We want to show that the limit is a. So we want this to be small. How can we do it? Well, we introduce the middleman. What is the middleman? A and k is going to be the middleman. So I added and subtracted that. Then I use triangle inequality. Right? Now, because this one is bigger than n2, I can use this inequality over here. So this will be less than epsilon over 2. And this one, remember, I'm calling it m. So this is the same as, let me write it over here. I'm going to repeat it for clarity. So this is an minus am, if we revert back to the m, plus ank minus a. And we can indeed use that m because nk is bigger than n1. That's the part that I told you we needed to use. So because both n and m are bigger than n1, then I can use this one here and this one here. So this is less than epsilon over 2 plus epsilon over 2, which is epsilon. And that's the end of it, right? We proved that the sequence an, not the subsequence, but the sequence an gets us close to a as we want. Epsilon close if you pick an n sufficiently large. All right? Okay, questions? All right. Now, the book has an interesting discussion at the end of this section, section 2.5, where they talk about the logical consequences, right? Specifically, we chose this axiom, the axiom of completeness, to define the real numbers. And it has an interesting it has an interesting discussion of maybe we could have chosen something else. For example, maybe we could have chosen the nested interval property. The nested interval property. And it turns out that that's not enough. You need the nested interval. If you want to use the nested interval property, you also need to add the Archimedean property. If you put those two together, then yes, you can show the axiom of completeness. And then there's several equivalences there that you can establish, okay? Now, it's interesting. You can take a look at it and read it on your own if you want to, but it's not central to what we're studying here. Because remember, our approach here was to put the axiom of completeness as something that could somehow tell us that the reals have no holes, and then move up from there. But later on, if not in our course, unfortunately, but if you take a more advanced course, you could actually construct the real numbers with a variety of techniques, and then show that the axiom of completeness is satisfied. And then we're good, because that's that was our starting point. Then everything we prove from there is going to make perfect sense anyways. Okay? So I will not get into the logical possible equivalences there at the end of section 2.5, but you're welcome to take a look at them. There's I meant section 2.6. They're really interesting, definitely. Instead, what we're going to do is continue talking about series, right? So we did very little on series. We wrote down what it means for a series to be convergent, and we presented a couple of examples, the harmonic one and the 1 over n squared, and we did the p-series criterion, right, using the compressed Cauchy criterion. That was also a nice thing. So today we're gonna go back to that, and that's the next section. It's called Properties of Infinite Series 2.7. And let me just remind you that to define whether a series converges or not, we use the sequence of partial sums, right? So recall that a series AK from 1 to infinity converges if its sequence Sm, which is the sum from 1 to m of partial sums, converges. That was our definition, all right? And just using that, we can establish this first theorem of basic properties. You'll see them, and you'll right away should get an idea of how you could prove this. And it says the following, theorem 2.7.1, if you have two convergent sequences, one of them converges to A, and the other one converges to B, then one, if you create a new sequence where you multiply by a constant, these will be convergent, and you're gonna get C times A as the answer. That's for an arbitrary real constant. And two, if you create a new series that consists of the sum of the elements of the one with the elements of the other, right, adding corresponding terms, this one will be convergent, and the answer will be what you expect, the sum of the two other ones, right? So basic properties, like I said, this you could call these the that series are like if you take a linear algebra, this is like a vector space, right? Like adding things together and multiplying by a constant. Mm-hmm.
Professor, can you move up a little bit? I just wanted to see that above.
You mean move down?
Oh yeah, sorry.
Yeah. Yeah. So we'll prove this, and of course the proof will be based on the partial sums, right? So we have them defined right here. I'm just going to repeat that writing here. So let Sm be from k equals 1 to m of AK. Okay, and then all we need to do is to prove that the corresponding partial sums for this new series are convergent, right? And how can we do that? Well, we just need the algebraic, I mean, we sort of did these properties for sequences, right? And think about it. Series are defined in terms of sequences. So all you need to do is take the series, write down what is the sequence you need to study, use the properties of sequences we know, like the algebraic limit theorem we proved, and then revert it back to what it says about a series. And it's as easy as that. So for example, by the algebraic limit theorem, we already know that the limit of CSM is C times the limit of SM, right? But we can take constants out. And this one is C times capital A, because we know that these guys are convergent to A. That's by assumption, correct? So then we're done, right? Because then that means these partial sums. So, however, what is C times SM? C times SM is C times this finite sum. But this is a finite sum, so I can use the distributive property and multiply. If you want to multiply C times a sum as C times the first plus C times the second, etc. So this is the same as CAK from 1 to m, right? And these are precisely the partial sums of the series we want. So the partial sums of the series we want are C times SM. And we know that the limit of those exists and is equal to CA. So we're done. Thus, this series converges and it equals C times A. So I'll just write here in parentheses, that is CSM is the partial sum of CAK, the series. Okay, so that's the proof of the first one. The second one goes along the same way. So now we now need to introduce not only the partial sums of the A's, but also the partial sums of the B's. So let's start with that. So I'm going to use T's for the other one. Let T sub N or sub M, let's keep the M, be the one where we use the B's. So it's a partial sum for the B's.
Was that up above the limit of the partial sums?
Say that again.
Where it says CSM is the partial sum?
Is the partial sum of the series, right? What? I don't understand what's bothering you.
Oh, so so it's not the limit of the partial sums. It's the partial sum.
So when we say the partial sum, we refer to a series, right? So if I talk about the partial sum of this infinite series, I mean the one that starts at 1 and stops at m.
Right, right.
Yeah. So that's what I wrote here, that this guy, so I'm not saying that these two are equal, if that's what's giving you problems here. Right? That's probably what is troubling you, because on the line on the top, I have that CSM is this guy over here. What I meant to say here is that this, by definition, CSM is the partial sum of these.
Okay.
Okay, so let's do the other one. It'll be very similar. So again, we use the algebraic limit theorem. So by algebraic limit theorem for sequences, we know that the limit of SM plus TM is equal to the limit of the SM plus the limit of the TM, right? And that's A and that's B. Those two exist and they're equal A plus B. And so that's great. Now I'm only gonna argue that this is the partial sum of the, where should I put it here? Right here, of this series, all right? So how do we do that? Well, note that if I add up from k equals 1 to m, ak plus bk, well, this is a finite sum. So for finite sums, it's okay for me to break it into first adding the a's and then adding the b's. So this is precisely sm plus tm. So the partial sums of the infinite series are sm plus tm. So hence, the partial sums of the infinite series are Sm plus Tm. Where m ranges over all the natural numbers. And we already know that these guys have a limit. It's written right here. They have a limit, and the answer to the limit is a plus b. So this is a convergent sequence. And because this is a convergent sequence, that means the series is convergent. Thus, the series converges. and equals a plus b, right? It equals the value of this limit, which we established was a plus b, all right? Easy, like I said. I mean, this is like how can we use the properties of sequences that we know to create properties of series. And then we're going to take this one step ahead, and we're going to write down this that we just learned, the Cauchy criterion for series. So that's what this is called, Cauchy criterion for series. And what it is just the following. You can write down, so it's as follows. We know that a series converges if the partial sums, the sequence of partial sums converges. And we know that the sequence of partial sums converges if and only if the sequence of partial sums is Cauchy. So what is the meaning of the sequence of partial sums being Cauchy? Is what we're going to write down, essentially. All right? So, and this is what it says. It says that the series from 1 to infinity converges if and only if given epsilon greater than 0, there is capital N, a natural number, such that am plus 1 plus am plus 2 plus an is less than epsilon whenever n is bigger than m, which is greater than or equal capital N. Oof. Right there. And this is precisely what it means for the sequence of partial sums to be Cauchy. That's going to be the proof. So the proof is actually very, very simple, because it's just writing down what we knew before, right? Yeah, it's based, the Cauchy criterion for series is heavily based in the Cauchy criterion for sequences. Okay, so here we go, proof. We first define the partial sums. So let S sub t be from k equals 1 to t of a sub t, right? So we know that, then this is the part that I was telling you about, we know that this converges, the series, if and only if the partial sums are convergent. The sequence of partial sum converges. And this is if and only if the partial sums is Cauchy. This is by the Cauchy criterion for sequences, or simply the Cauchy criterion, the basic one, right? So if and only if this one. Okay, and what is the meaning of this one? What is the meaning of a sequence being Cauchy? Well, let's write it down. It means that for every epsilon, there exists some capital N, such that if little n and little m are bigger than capital N, then the sequence Sn minus Sm is less than epsilon, right? That's the definition of being Cauchy. I just wrote it down. Now, here we need to do something a little bit different, because here it didn't matter, right? You pick two of them, n and m, and as long as they're bigger than n, you're good, right? Now, here, let's do it a little bit differently. So let's change this. Let's change this and instead ask that n is bigger than m, and so in other words, pick n as the largest, right? You're picking two of them, and arbitrarily, let's say that n is the larger one. Now, maybe you're wondering, hey, professor, what if they are equal? What if n equals m? Well, if they are equal, then the difference is 0, right? Sn minus Sm would be 0. And that's true no matter what, because epsilon is greater than 0. So we don't need to care about that one, right? If they're equal, it's a vacuum statement. We're not saying anything important. So we can forget about that case and assume that one of them is larger. And the larger one, we can call it capital N, right? So instead of writing it this way, we can write it like this, and it's equivalent. Okay, and then all that I need to do to show you that we got the same thing is to show you what this is. What is Sn minus Sm? And so here we go. But what is that? What is Sn minus Sm? Well, let's write down the definition. Sn was the sum of the a sub t's from 1 to n. And this one was the sum from 1 to m, right? Now you see why we picked them this way, because this one, n, is bigger, right? This one has more terms than this one. So a lot of things are going to cancel, right? So, for example, A1 will cancel because you have A1 here, and it's also in here with a negative sign. So A1 will cancel. Maybe the second one will cancel too, etc. So what are the ones that are going to survive? Well, the ones that are going to survive are, so all of these are going to cancel because m is smaller than n. So the first one after this will survive. So that's a sub m plus 1. And then the one after that, and all the way to an, right? And that's the end of my proof, right? Because that's the property that I wanted. I wanted this to be less than epsilon. That's what is written right here at the top, right? So we know that this is less than epsilon, and that's the property we wanted. So to put it in lay terms, if I could, would be that a series is convergent if the tail, if you can pick a tail, right? This is like a tail from a very large number to a number even bigger than that. If you can make the tails arbitrarily small, right? The sum of the tails, right? This is what I'm calling the tail. Right? So I have a series, and I'm picking it from n plus 1 to n. That's a little tail. If I can make the tail as small as I want, no matter how, so if for every epsilon, you tell me how small you want it, I can pick a large enough entry point, and then if you take any tail that starts to the right of that, so that's the capital N, to the right of capital N, so n plus 1, and stops wherever you want, if you make that smaller than epsilon, then the series converges, right? That's the Cauchy criterion. All right. And just to finish for today, let's apply it. Let's give a very specific application of this one. Something that you're familiar with, as a matter of fact. You may remember it as the divergence test, right? It's a very quick way to know if a series diverges or not. So this is theorem 2.7.3. It's called the divergence test. How do we check if a series diverges quickly? Well, if the terms don't go to 0, right? So this is what it says. It says if you have a series that converges, then the sequence goes to 0, right? The terms themselves go to 0. And we actually use it as in calculus in 150B, when you learn this for the first time, we actually use it the other way around. So equivalently, let me write it like that. Equivalently, if AK is not going to 0, if the limit of the AK is not 0, then the series is not convergent. Diverges. And that's why we call it the divergence test, because that's the first thing you check, right? You check if the terms are going to 0. If the terms are not going to 0, you know it diverges automatically, right? Okay. And how do we prove this? Super easy proof. We're just going to apply the Cauchy criterion. Proof. Because, well, that's okay. let me start by giving my assumption. So I'm going to prove the top one, not the bottom one. Okay, so I'm going to prove it in this form. If the series converges, then this happens. So assume the series converges. So because it converges, I can use the Cauchy criterion for series. Then by the Cauchy criterion, given epsilon greater than 0, there is some capital N, a natural number, such that if little n is bigger than capital M, which is bigger than capital N, then this little tail is smaller than epsilon, right? That's what the Cauchy criterion says. And now I'm not going to use the entirety of the Cauchy criterion. I'm just going to use a particular case of it. So this works for any little n and any little m, right? So here's what we're going to do. We're going to pick only one of these terms, right? So let little, which one I want? Hold on just a sec. Let little n be m plus 1. So let's just use the next one after this, right? So then that means instead of having a big tail here, I'm only having the first term. It's only going to be this one. Then for little m bigger than capital N, we have that a sub m plus 1 is smaller than epsilon. And think about it. What is it that we just proved here? You gave me an epsilon, an arbitrary epsilon, and I found a capital N. And if your little number is bigger than capital N, then this is less than epsilon, right? So in other words, we just proved that the limit of a m plus 1 is 0, right? So this sequence is 0. And we've established before that it doesn't matter that says m plus 1. This is just like the same sequence am. It's only going 1 unit ahead, right? It starts at 2 instead of at a2 instead of starting at a1. But the limit is about the end behavior. So I don't care where it starts, right? So I can just write here, that is, the limit of am is 0, just like we wanted to prove, right? Okay, and I don't want to rush through the next ones, the next few, so I'm going to stop right here. So there are other series that, tests that you're familiar with that we're going to prove the same way. So for instance, you may remember the comparison test, right? You use that to compare two series and see which one was convergent and which one is not. The absolute convergence test, the alternating series test, and so on. All of them can be proved using the Cauchy criterion in a very easy and straightforward way. So we're going to do that next class, finish chapter 2, and give it a start on chapter 3, which is actually quite interesting. We have the introduction part is nice. You'll learn something new, hopefully, and interesting on its own. All right, so I'll stop right here, and I'll see you guys on Wednesday.
Thank you, Professor.
Thank you,
Yeah.
Professor.
See you guys.
All right, see you, Professor.